Hello everyone. We're going to do a couple examples to go over finding probabilities using the normal distribution, and specifically using the standard normal probability distribution and a standard normal table. So I actually have a table here, but you'll want to reference the prior video where we discussed how you actually use this table. Now, a couple things I wanted to remind you about before we begin doing these probabilities is that what we're doing is we are transforming from our actual normal distribution to the standard normal distribution. This gets us in a standardized specific distribution that then allows us to use this table to find the probabilities to the left of a positive value. Now, again, they are approximations, so they won't be as exact as if you then practiced doing integration to actually get the actual probability. So the first problem says, suppose that a random variable x follows a normal distribution with a mean of 36 and a standard deviation of 4. So we have a mean of 36 and a standard deviation of 4. What is the probability that a data point observed is at most 45.15? So we have the probability of x, and then we know that our value is 45.15. And we need to figure out, what does it mean to be at most 45.15? And this means less than or equal to. We want a value that can be up to and including 45.15 and anything less. So what we're going to do now is we're in terms of x. This is our normal distribution, which is centered at 36 and has a standard deviation of 4. And we want to transform this to our standard normal, which has the center at 0 and a standard deviation of 1. So we're going to do this using our z transformation, which, if you remember, our z transformation is just that z equals x minus mu over sigma. So we're going to do this transformation on our x. So we have the probability of x, and then we're going to subtract mu, divide by sigma. We're going to leave our sign the same. And then we're going to do the same thing to this. We're going to take this value, which is our x value, 45.15, minus, now we're going to subtract mu. Mu is 36. And then we're going to divide by sigma, which is 4. This is going to give us the probability of, now we have x minus mu over sigma, which we just said is z. So now we're going to replace that with z, because once we've transformed from our normal distribution, which is in terms of x, once we get to our standard normal, this is oftentimes called the z distribution. And this table is often called a z table, because that is the symbol we use for standard normal. Our sign stays the same. So we get 45.15 minus 36 divided by 4. Now, our table will always be in terms of 2 decimal places, because along the left side, we have the units, so 1, 2, or 3, or 0. We have the tenths place, which can be anything from 0.0 all the way down to 0.9. And then along the top, we have the hundredths place, which could be anything from 0.00 to 0.09, meaning that we will get a value that is rounded to 2.29. Now, once we have it at this point, this is when we have to determine, do we need to do any transformations to get it in the form that we need for this table? Well, 2.29 is a positive value, and we're looking to the left. This means that we can just look it up in our table. So to do this, what we're going to do is we're going to go down to 2.2, so it's right here, and then I'm going to go all the way over to 0.09, which corresponds with 0.09 up here at the top, and this is going to give me 0.9890. So this means that if the mean is 36 and the standard deviation is 4, the probability that I would get a value that is less than or equal to 45.15 is 0.9890, or about 98.9% chance. The second problem asked, what is the probability the data point observed is at least 32.65? So we have the probability that x is at least, so greater than or equal to, 32.65. And we're going to do the same process to figure out what this probability is. We're first going to do our z transformation. So this becomes probability of x minus mu over sigma, greater than or equal to, the sign doesn't change, and then we're going to plug in our values. 32.65 minus 36 divided by our sigma, which is 4. Now, one thing you could look at before you actually do this to double check yourself is when we were doing this first calculation, we had 45.15 minus 36. Well, on my normal distribution, 45.15 would be somewhere over here to the right of 36, meaning that I knew that the z value had to be something that's positive. If I look at this one, 32.65 is to the left of 36, meaning that the associated z value I'm going to get is going to be a negative. So when you do this calculation, you can double check whether it's positive or negative by whether your x value is larger than your mu, which means it'll be to the right, or is it less than mu, which means it'll be to the left. And if it's equal to mu, then this is actually a special case where you'll end up getting 0.5, because if I ask what is the probability to the left of mu or to the right of mu, it just accounts for half the data. So for this problem, though, we get the probability of x minus mu over sigma, that's z. My sign doesn't change, and the value I get is 0.84. Negative, because as we said, it is to the left of 36. Okay, so now, can I look this up in my table? Well, my z value is negative, so the answer is no. First thing I need to do is I need to use symmetry, right? Because I have this. I am looking at everything that is greater than or equal to negative 0.84. So I'm going to use symmetry to create a mirror image of this, and I'll be looking at everything to the left of 0.84. So this is going to be equal to the probability z is less than positive 0.84. Now this I can look up in my table because this value is positive and we're looking to the left. So doing that, we're going to go to our table. You're going to go down to 0.8. You're going to go over to 0.04, and we're going to get 0.7995. The next problem asks, what is the probability the data point observed is at most 27.5? So at most 27.5, so again, we do probability that x is at most, which means less than or equal to 27.5. We do our z transformation, probability x minus mu over sigma, sign stays the same, is going to be 27.5 minus my mu of 36, divided by my sigma of 4, and this is going to give me the probability that z is less than or equal to negative 2.13. Now let's double check that. Should this be a negative? Well, 27.5 is less than 36, so yeah, this looks good. So again, if I were to draw a quick little image, I have a negative value, and I'm looking to the left. When I mirror image this by symmetry, I'm going to be finding a value that is to the right of positive 2.13. So this is going to become the probability z is greater than or equal to 2.13. It is positive, but it's looking to the right, so I still need to do another transformation. So what I'm going to do is I'm now going to use my complement, which is, of course, take the entire distribution, subtract off everything to the left of that positive value, and I'll be left with the probability that is to the right of that positive value, which is equivalent to the probability to the left of the negative value. So this is going to end up being 1 minus the probability z is less than 2.13. We have a positive value. We have it going to the left. So therefore, we can look this up in our table. So we go to our table. We go down to 2.1. We go over to 0.03, and we get 0.9834. So this is going to be equal to 1 minus 0.9834. And then we just solve. What is 1 minus 0.9834? It would be 0.0166. Now, the last problem asks, what is the probability that the data point observed is at least 44? So the probability x is at least, so greater than or equal to 44. we do our transformation. So probability of x minus mu over sigma is greater than or equal to 44 minus 36 divided by 4. This is going to be equal to the probability that z is greater than or equal to 2.0. Okay, I have a positive value, but it's looking to the right. So what I'm going to use the complement. So this is going to be equal to 1 minus the probability z is less than 2.0. Now, whenever you get a value that does not have two decimal places, for example, let's say we got 2.1, or in this case, 2.0. What you're going to do is you're just going to go to the zeros. So in this case, we have 2.0, so we go down to 2.0. We go over to the first column, which is 0.00, and we get 0.9772. So we get 1 minus 0.9772, which is going to be equal to 0.0228. You can see here from our slides that this is what it looks like when you're looking these up. And you can actually see an example of each of the z-table lookups that we did on our prior problem. Let's go to another example. Given that the coffee consumption per day by college-going students follows a normal distribution with a mean of 2.25 cups of coffee, so we have mu equals 2.25, and a standard deviation of sigma equals 0.25. The first problem asks us to find the probability a selected student will consume less than 2 cups of coffee. So we want the probability that some random student that we select consumes less than 2 cups of coffee. And it could be less than or could be less than or equal to, because as I said previously, for a continuous probability distribution, the equals to doesn't change it. So the problem says less than, so I'm not doing the equals to, even though the slide shows an equals to. So we're going to do our z transformation. So this is going to be the probability of x minus mu over sigma is less than, and now we're going to plug in our mu and our sigma into this. So we get 2 minus 2.25 divided by 0.25. In this example, you will see that 2 is less than 2.25, meaning we know we should get a negative value. So 2 minus 2.25 is going to give us negative 0.25 divided by 0.25, which means we'll get a probability that z is less than negative 1. Because we have a negative, we have to use symmetry. Now, when you use symmetry, if I'm not going to draw my images, what you need to do is when this negative 1 becomes positive, you need to flip the sign. So this is going to be equivalent to the probability z is greater than positive 1. We have a positive value now, but we're looking to the right, which means we need to use the complement. 1 minus the probability z is less than positive 1. So this will end up being 1 minus, and we go to our table. We look up 1.0, we go over to the first column for 0, 0, and we get 0.8413, which will be 0.1587. The next problem asks, what is the probability that the selected student will consume more than 1.5 cups of coffee? So they consume more than 1.5. So again, we do our z transformation, x minus mu over sigma. Sign stays the same. Plug in your values, 1.5 minus 2.25 divided by 0.25. In this case, 1.5 minus 2.25 would be negative 0.75 divided by 0.25, which is going to give us the probability that z, sign stays the same, so greater than negative 3. So we have a negative value, and what we need to do is we need to mirror image it so we have a positive value. So we're looking to the right of a negative. When we mirror image it, we'll be looking to the left of the positive, right? Because the sign changes, so this becomes less than, and then the sign on this changes. We have a positive value. It's looking to the left. We can look this up in our table. So this is going to be equal to, we go in our table, go to 3.00, we get 0.9987. Then the last example is find the probability the selected student will consume between 2 and 3 cups of coffee. So in this one, we have that the probability that they will consume somewhere between 2 and 3 cups of coffee. And we could do, again, could be greater than or equal to 2 or less than or equal to 3, it doesn't matter. So what we're going to do in this case is we're going to do the same steps, but we need to keep track of our lower value and our upper value. So this is going to be the probability that 2 minus 2.25 divided by 0.25 is less than x minus mu over sigma is less than 3 minus 2.25 divided by 0.25, which is going to be equal to the probability -1 is less than z is less than positive 3. We're going to use the case where when we have probability of z between two values, we split it by taking the probability that z is less than the larger value, 3, minus the probability that z is less than the smaller value, -1. This first one, probability of z is less than 3, I can look this up in my table. This one, I cannot. It is looking to the left of a negative value. So what I need to do first is I need to use symmetry to flip it to the right of a positive value. But again, I can't look up a value looking to the right of a positive value, so I need to use the complement to get to the left of the positive value. So this is going to end up being the probability that z is less than 3 minus 1 minus the probability z is less than positive 1. And I can look this up in my table. So first thing we'll do, probability z is less than 3. I don't even need to look this up in my table because we literally just did this in this problem right here. We have the probability z is less than 3, gave us 0.9987. Minus, and then we have 1 minus probability z is less than 1. Well, guess what? We have that also. We had that from the first problem. This was equal to 0.8413. Which, again, we also have this next part in the original problem. So this is 0.9987 minus, well, 1 minus 0.8413 is 0.1587. So 0.9987 minus 0.1587 is going to give us 0.84. There's one last thing I want to talk about before we move on from this topic, and that is, what do you do if you get a value that is beyond what's on this table? So you'll notice that this table only goes up to 3.49, meaning using this table, you can only find probabilities for z less than or equal to 3.49. I'm going to put equals to because it can be equal to 3.49. So what do you do if you get a value that's beyond that? Let's say you get probability z is less than 6.22. What do you do? Well, if you notice what happens, as your probability approaches 3.49, we have a probability of 0.9998, meaning that only 0.0002 of the data falls to the right of that. So pretty much the rule we're going to use for this class is that if you have the probability, I'm going to use 6.22 just as some stand-in value, but any value that's greater than or beyond 3.49. If the probability z is less than or equal to 6.22, which would be something like this, way down here, and it's everything to the left, this pretty much accounts for everything. So we're just going to round it to 1. It's not exactly 1, but because we're limited by this tool and we're not finding the actual probability by calculating it, we don't have the actual specific information. We don't know if it's 0.9999998. We don't know if it's 0.99999999998 or anything like that. We just know that at that point, it's so small that we're just going to assume that it's roughly 1. If we have the probability that z is greater than or equal to 6.22, this would be the case where we have our normal distribution, our standard normal, and we have a value way out here, and we're looking at everything to the right of it. Well, kind of the inverse of the first example. When we were looking to the left of it, we said it was roughly 1. So to the right of it is going to be roughly equal to 0. If we have negative values, if we have the probability z is greater than or equal to negative 6.22, right? Because this is going to follow by the same thing with symmetry. This would be if I have everything to the left of some value way out here, and I look to the right, this is going to be pretty much everything, right? And if I did symmetry, it would be this first case. So this would be equal to 1. And then if I had the probability z is less than or equal to negative 6.22, this would be looking at what's the probability of this little bit down here. We're going to say that it's roughly equivalent to 0. So that's it for all of the topic from this. There is actually one last thing I wanted to mention, more just because you might find it useful and or interesting. So give me a second to clean this up and I'll tell you about it. In the last example we did, where we were finding what is the probability that 2 is less than x is less than 3, what we did is we converted this to z by finding the probability that negative 1 is less than z was less than 3. And we did this by first converting to z, and then we split this to the probability z is less than the bigger number minus the probability z is less than the smaller number. You can actually do the split when it's in terms of x as well for your normal distribution. So we can still split it the same way, where this would be the probability of x is less than the bigger number 3 minus the probability that x is less than the smaller number 2. And then here what you would do is you would do your z transformation from there, focusing just on the individual pieces. So this first one would have been probability x minus mu over sigma is less than 3 minus 2.25 divided by 0.25. This part would be probability x minus mu over sigma is less than 2 minus 2.25 divided by 0.25, which would give us probability z is less than 3 minus the probability that z is less than negative 1. And you'll see that this is actually equivalent to what we had done when we split it after doing the z transformation. You can actually do the z transformation you actually can do the split first, followed by the z transformation. And the last thing I wanted to say as we finish up this section and all of chapter 5 is that remember that when we're dealing with this, when you are in your normal distribution, which is centered on mu with a standard deviation of sigma, your value that you were using, your random variable, is x. Once you've done the transformation and you are on the standard normal, which is the normal distribution centered at 1 with a standard deviation, centered at 0 with a standard deviation of 1, then you were in terms of z. You need to keep this in mind because when we are going from our normal distribution to the standard normal, we are transforming from x as a random variable to the z value. In the next section, we're going to be looking at what if we actually have this and we're trying to figure out what x value would make that happen. So you do need to keep track of x is your random variable on the actual data space. This would be the cups of coffee, the height of basketball players, the GPA of students. Whatever this data represents, x is your random variable. Z is the standardized z value that is equivalent on the standard normal distribution to your value, but the actual data space, this is where your actual data lies. What you're doing is doing a transformation to get it in terms of a standard normal so that we can then use this table to find the probabilities of some interval on it. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.